I doubt I can share these recordings. So those who are present can learn. Otherwise, everyone is ready. Okay. From like how many? Around 170 students. So 100 are missing. So I should share. I should stop sharing the recording. Although being it is continue. Those who are there will learn. There is God bless you, right? You should from home. They don't manage to make it on time. So if you want a good grade and everything is fine and you are healthy, at least you should come on time. Okay, so last time we did a few examples and you are well good. I was happy to know that. And we were with this kind of slides. So anybody, any query up till now?
Ma'am, I have doubt in slide number 34.
Yeah. Yes, please.
No, ma'am, not this one. Like determining diode current graphically.
Yeah, I'll explain you. So don't worry. I'll start with this point, although I had spoken last time. Okay. So now we have to build circuits. Okay. And we have to, it's all about I and V. How much voltage? Because see, every application has a different voltage, different current flows, or because of the change in the current, there's a change in the voltage and vice versa. Okay. So, and the diode has its own IV curve. I mean, IV characteristics or its own nature. You are changing V, and for that specific V, you will have a specific current every time you operate the diode at that voltage, right? You agree with that? So you know this curve exponential of the diode, right? So this is an expanded view. Sorry. Yeah. So there is a corresponding current for every voltage. So every time you operate for this voltage, you will get this current only. And for this voltage, you will get this current only. And when you build circuits, we have to exactly calculate. There is a need that you have to calculate for different operating voltages. The voltage can be from few volt to hundreds of volts. Okay. And so with that thing, now what I explained you last time is this shows the IV of, it is plotted and it is showing the concept here that let's say that there is a diode and there is a DC voltage which has a signal superimposed. So this signal is the signal that you want to process. See, everything you are doing, that is because you want to process the signal of your interest. For example, right now I am speaking from a microphone. Okay, we amplify microphone signal, right? It's not that we will rectify it, but any small signal out of a sensor, let's say. So these are very weak signals. In some the current is in milliampere or the voltage is in millivolt. Okay, so here we are talking in terms of voltage, that there is a very weak signal in form of a voltage, and that is in millivolt. And if you want to rectify that, then what we will do, we will superimpose onto a DC source, because if you want to, now you want to pass it through a diode. Okay, so it is conducting, and then you know when it is not conducting and when it is conducting. So now when the small signal, if you want to pass through a diode, this is in millivolt, and let's say this is the diode curve, as you know. Now, if this is signal which is very weak, right? So if this is in this range, this signal is in this range, let's say, then what? Then hardly any current will flow because diode is off. It is hardly any current means it is off only, nanoampere or pico, the leakage current we say. Do you understand? So what we do, we make the diode, because if this is the circuit and you have to have the current flowing through the loop, right? Then you have to make the diode on first. The diode is off, it's all, this is open, no sense. The diode has to be on. To make diode on, when you want to process a very low voltage signal, we give some voltage. This voltage is known as bias. That is, you are giving a proper circumstances, situation or condition, so that it is first alive, it is first on, it is first conducting. Okay. If the diode is dead, means if it is off, then no sense, it will not process the signal. So this is the case when your voltage is very low. These are low voltages, millivolt, and it is of the order of VT. Okay, so VT is 25.8 millivolt for a room temperature when this voltage is of that order. So then what happens? In that case, these two voltages are superimposed. First, if you make this zero, let's say, if you are making this zero, then your curve will be, this is your diode curve, this is V, this is I, and this voltage, let's say. Okay, so let's say this voltage, that is your VD. It is written VD, right? And that VD is, let's say, 0.7 volt. Okay, so this center line you see is VD. It is 0.7 volt. If this is zero, then for that VD, right, some current will flow. Okay, this ID. But now this is an AC signal. Let's say here we are taking triangular wave. So that will be added to this signal. And as you can know, it will fluctuate at this 0.7 volt plus minus. Okay. And then for this kind of a signal, right, for this point, when the voltage is here, this current will flow. When the voltage maximum is here, this current will flow. So your current is fluctuating between this point and this point, as you can see here. Okay, so for your voltage that is for this point, it is this point. So for voltage that is fluctuating, your output is following the input, because your input is varying for a very small change, you can say, very in millivolt the changes. If the change would have been greater, let's say I would have this kind of curve. If the change is greater, like this, right, then this is falling here, and this guy is falling here. You will use this thing, but this itself is non-linear. So whatever you will, whatever your curve is, it will not follow your output current. The diode current will not follow linearly. It may be like this is elongated, this half, and this, so something like that. Okay, it will not follow linearly. If it is a sine wave, it will not give exact sine wave or exact. So the point is that because this itself is non-linear, this curve itself is non-linear. So we choose, if the signal is very small, you bias the diode, first make it conducting and giving proper voltage, that is 0.7 here. And we ensure that this is a little change where this, the tangent, the line that is here, right? So this slope is almost constant. Okay, where this is falling, this slope has to be almost the same. Then and then you will get your ID proportional to or varying as per your voltage, this voltage. So that's the goal. And so because if it is a bigger voltage, then it is going to, and then let's say if there is no bias at all and this voltage is still greater, let's say, then this your input is from, so if this is not there at all and this is fluctuating, let's say from 0 to 0.7, this is, let's say, 0 to 1.7, right? Then for all of this you will not get any output. Up to here, up to this much, around up to this much volt, you will not get any output, only of your input. So what you will get is this, then this point will be here. So I mean, your signal is distorted, your current, which is traveling, as I explained you last time. Your signal is traveling in form of current. And if your current is not proportional to your input signal, then at the output you get something. For example, I'm speaking now, the amplifier which is amplifying the signal is linear. Okay, so for low amplitude or high amplitude, it will amplify same with same factor, multiplication factor, okay, amplification factor. But if it is behaving non-linearly, then you will see that if my tone is not equal, okay, it will vary. That's what. So it has to be linear. That's what it is showing here. So this is for a small signal. Okay, when we are operating a diode with a small signal, please mute your microphone. Who is there? You mute your microphone, please. Here, this is for a small signal where we bias the diode first to make it conduct, and that is 0.7 volt here, for example. Okay, and then now we have to, now this diode is never, I mean, we don't directly connect to the supply, okay? There is a resistor which will protect the diode, because if the current is very high, so if the voltage is high current will flow, it will get destroyed, okay? So the diode should be biased, the diode should be protected, and there is a resistor in the circuit. So that is this resistor, which will protect the diode from getting destroyed. Hello? Are you, am I audible? Are you understanding?
Yes, ma'am.
So this is not a
Yes,
practical circuit. This is a practical circuit now. So there is a resistor, and this is just a one loop and a simple circuit where you have diode connected to R. Now we have to determine the current. Now you understand one thing. When you apply a DC voltage, it is fixed. When you give R, it is fixed. What is changing here in this? See, this is fixed. And understand, in electronics, there are nothing more. You have like 3 to 4 cards only in 2 basics. I, V, R, C. Even L we don't use much. A voltage source. We don't have, you can count on your fingertips. इसमें हर फर्क है क्या? So here, now VDD is DC, you understand, this is fixed. This is fixed. Right? If there is a fluctuation, let's say from here it will fluctuate plus or minus 10%. Then this will be VDD plus some volt, VDD minus some volt, let's say. But this is DC, whatever it is. From here it may fluctuate, let's say, little. But at a time it is DC, okay. So what will change here? Another thing, let's see if this is your diode curve. What is this V and I? This I and this V? Here, this is more better. This V and this I. What is that? Which one is that?
Madam,
If
V
I'm
is the
plotting
current and
voltage across the diode, and I is current across the diode.
Very good. So this you should be clear. This voltage is across the diode. Okay, this voltage is across the diode, these 2 points. That you should be clear, and that is this I. Now I'm coming here. The very basic things, but it has to be clear. Now this is, let's say, 1 volt. Okay, then what is flowing here? And this is fixed. Then, and then if this is 2 volt, then what is the difference? And another thing, this is a loop. through a loop, a same current flows. So whatever is flowing through this will flow through this also. The whole thing, ID is only flowing. Okay, the same current. And for diode, it is obeying this curve, as you have seen. So for a diode, for a change in this voltage across the diode, for a change in voltage across the diode, if this is changing this way, this voltage is changing this way, and if it is here, only this current will pass. If it is here, only this current will pass. That way, the resistor also has a characteristics. If the line is like for R, if instead of this, you have a R. Okay, instead of a diode, if you have to plot for R, this is separate. I'm just showing you separately R. Then the line will be like this depending on R, but it will be linear line. And for this voltage, only one R will, for one voltage, only some current. For a particular value, another value of R, it can be this way. Okay, so this is R1, this is R2, let's say. So for this voltage, only this current will pass, and for this voltage through R2, only this current will pass. So this is also fixed for R. Now you have R and D both. So what is changing here now? So now you have R and D both. Yeah, so you have R and D both. So this current, what is passing through this whole thing is saying it should satisfy. Now remember, it should satisfy this characteristics also and this characteristics also. So it should be a common point. Now you must understand that in this universe, the nature is very intelligent. So what will change here is depending on this. Okay, this is changing. If you change R from R1 to R2, this guy will change such that it will satisfy both of them. So this is automatic thing that I will change as per this R and the voltage and the R of this dynamic resistance of this. So and if the voltage is also changing, accordingly the current will change. Okay, so I is changing if other things are fixed. So if now you imagine, now we have to find out I. Okay, so there are two ways of doing. One is equations by mathematics. Okay, but if you understand, then you apply mathematics. To understand, we will see the graph. But every time to solve a problem, you will not draw a graph. You will do it by an equation, provided you have understood. To understand, we will see the graph. Now, this can be shown graphically also. How? That's what I'm going to teach you. So now, for when this is conducting and the current is high, that exponential equation, this IS, which is of the order of nano ampere IS, right? When it is conducting, right? This ID is very, very greater than IS. So that minus one term in that equation, this. So when it is conducting, IS is saturation and it is there. This is the range. So when it is conducting, this I is in milliampere. This is in pico, nano pico ampere, less than nano, around pico ampere. So this is very, very higher than IS, and in that case, we can neglect this minus one term. And that's why we are using that equation without minus one term, because it is conducting, and this is the equation of ID. And again, ID can be also given by this equation, you know, that this is this voltage, which is there. You can think like as a battery, okay, replace it. So it is this voltage minus this voltage divided by R. So both of this equation, this ID can hold, it should hold, right? And if you change R, then also ID will change. So it is the current that is, this is we don't control. It is happening on its own. The I changes ID. This I changes as per this V, then R. If you change R, if you change VDD, I will change automatically. We have no control. The nature has made the material, the universe that way. So this guy is changing. So if you plot this is your diode curve, that is this curve. Okay, so when it is conducting and this is your diode curve, you can put minus one, no problem. This is just an approximation. Because it is conducting, you can neglect that. And this you draw, right? So when you are drawing this, so that is, these are two equations. This is your diode voltage, this is your diode current, and two equations, two unknown. And if you plot for this, right? So this is if you plot of this graph of this one, sorry, this one. Okay, so this is your V, and this is your I. Okay, and your V, we are changing from 0 to VDD. Okay, let's say. So here, this is your supply. Okay, and this is your diode. This now this V is you are changing from 0 to VDD. And here, this is this graph, and when you plot, so this is here, V is 0, here I is 0 horizontal. When you plot, you will get this line here, which is cutting I at VDD by R. In this equation, if you put one time this as 0 and do, you will get, you move this side and you will get for I and V where it intersects here. Okay, so you will get this line. And as said, this is known as the load line. And where it intersects this is the operating point. So here, but for this R, it will be here, it will be this line. If the R is changing, let's say to another value, it can be this line. If it is something else value, it can again go and cut here. It can be this line, okay? So where it cuts this, okay, is the operating point. So this current, this I, that is, as I said, okay, if it is this line, it is this I. If it is this line, it is this I. So this, if you change R, automatically that current will flow, which is satisfying both of them. We don't have to control the current. Okay, and the voltage accordingly for VD will be that. It will be little, it is not a drastic change as you know, but yes, it is different for a change in a current. So that's what, and that common point or intersecting point is the operating point. That is your, the diode voltage will be this and the current flowing will be this. You cannot have any other current flowing, right? Because if you take this voltage, then for R it is this current, and for this it is this, and then you have two different current. That is not possible in a single loop. So the nature, the nature does that, okay, that when you have this R and when you have this characteristic, accordingly by change, if you are changing R, as I just showed you, I will change automatically. हमको बैठ के कुछ नहीं करना है. So that common I will flow. Common current will flow, which will satisfy both of these equations.
Ma'am,
do you understand this much?
Ma'am, is this ideal diode or not ideal, non-ideal?
See, if it is anything in the world, is nothing is ideal. Why we took ideal initially? Just to keep things. We cannot go to the highest level of complexity. Here in diode, when you talk of this exponential curve and IV equation, and that is very precise. But as a beginner, we took it as an ideal diode to make things simple. Okay. But let's say if there is a device also like an ideal diode, what does it mean? That the voltage drop, the current will start flowing immediately. It is 0 volt, and 0 volt thoda cross kiya, so 0.001 volt, yeah, 0.1 volt, it will start conducting. And in non-ideal diode, it will conduct at 0.7 volt. So it is just this model that we used. Okay. If there is nothing in reality, ideal kuch nahi hai. Dekho. So this was the second level of approx. But let's say there is a device which is, a new device has come and which is acting like this. Okay, like an ideal diode. That can be today, in today's date, the diode curve is this. Yeah. But tomorrow there can be a new device that can come up and will have this curve. Then what does it mean that at the 0 volt the current starts flowing and there is no voltage drop? So what is the voltage, what is the resistance, that is you replace by that. So so this is for this constant voltage drop that is nearer to your real one. So this is for showing how the diode is connected or the direction of the current, and this is equal to 0.7, but this is still not the correct one. As I explained you, we use this model to make some rough estimate when we don't want exact current. हमको नहीं चाहिए. Not in all applications. In some, you just want to build a rectifier and you want to see whether the circuit will work fine or not. You are working at high voltages. That little drop will not matter, as I will show you now. Okay. So in that case, see now, for example, now, as I had showed you, okay, that this is a rectifier circuit. This circuit, you know, right? Simple. This is a rectifier circuit and this is some high voltage. We are not, so let's say 5 volt, 10 volt, like that, which is higher than the drop here. Then when you want to see that diagram, we don't want exact current, right? As we did here. As I was talking right now, we don't want this exact current. Right? Here, in this case, let's say you want an exact current, you will have to use this equation. But just to know whether the wave we get positive half, negative half, how it is behaving, you don't need an exact current. Then you can take this constant voltage drop model. Okay, so the way it depends on the analysis you want to do. You just want to see in terms of voltage, we don't want exact current. Then you plot it that, okay, 0.7 drop hua hai. Then वो थोड़ा 0.72 भी हुआ हो, 0.73 भी, you take this constant drop model. So it depends. Now we will see more examples, things will be clear to you. So it depends on the application. When you are working with high voltages and just want to make voltage analysis, you take this ideal or constant voltage drop model. So here also you took ideal. If it is constant voltage drop, then instead of 10 volt, you will have 10 minus 0.7, so 9.3. But when you are working with high voltages, let's say I'm talking of 100 volt, I'm giving here. And this is just 0.7. What will come out here is 99.3. So that is fine when I'm working with, I don't care about little drop. Do you understand my point?
Yes, ma'am.
But this device is applied, remember, this device is applied to here. Here, let's say in this case, the signal is in millivolt, small signal. And it is, if signal and you want to process it through a diode, and this is a small signal in millivolt, then what you cannot do, you can still do by using this bias. Giving an appropriate operating condition, you can still process this signal even if it is millivolt. And if it is already high volt, like as I showed you here, like this, if it is 100 volt and just one diode, right, 100 volt you are giving here and just one diode, and what you will get a practical case, which is realistic case, if you take, then it is 99.3 volt. So then you don't need biasing. You don't need this because here it is already high volt, it is operating, it is working. है ना? ये सिग्नल है, ये साइन वेव है, but ये बड़ी वेव है. This is really big. That this is always conducting for positive half, and that little drop is no matter. So you take as 100 only. So this is operating only. Little drop is nothing. 200 volt, 0.7 drop क्या है? कुछ नहीं है. So this output, this is shorted. It is when this we are talking of high volt, this is shorted. When it is conducting, it is shorted. So all this voltage, if it is, let's say this is 100 volt instead of 10 volt, then all this will appear here. So this output will follow input for all positive half, and for negative it is reverse biased. But it is conducting for, even if after 0.7 if you take, it's 0.7 is the drop, your output is just, so this is 100 volt, right? This is 0.7, this is 99.3. It's almost same. But if this is 0.7 millivolt instead of 100 volt, this is 10 millivolt. This is 10 millivolt. So for 10 millivolt, this is when you want to process this 10 millivolt. Instead of 100 volt, it is 10 millivolt. Then if you want to process this will be off only for 10 millivolt in practical case because it works at 0.7 volt. So if you want to process, if this is a signal out of a sensor and you want to process, then you have to bias it like this way. It's simple logic only. Anyhow, if you want to use a diode to process your signal, you have to make it conduct. When it is very low volt, you need a biasing. And if it is very high volt, you don't need this. Why you need it? Already it is conducting. So it depends on the application. And the current is changing as per R or as per your changing the VDD. Okay. So this is a simple case of a circuit application of a diode. And this is R is always there. And what changes is I. Automatically it will change. If my load line is like this way, okay, then accordingly this I will flow, which is common to both. It should be obeying this load line also and it should be obeying this also. We don't have to intervene and do anything with I. It will automatically, you change R, I will change automatically. And such that it will obey both of this equation. It's like, both.
Ma'am, here we will not consider the RD resistance of the diode for
yes,
this
yes,
equation.
yes. Good point.
It should
Yes,
be
you
R plus
RD
RD.
we consider. Yeah, see, if you are now, very good point. And again, as I said, it depends on what calculations you want to make. Now, let's say that these are your ideal diode model here when you consider this piecewise linear model, the slope here is 1 upon RD. And this is constant. Okay, it is an approximate of this. And if you are considering still this RD here, this is one RD1, this is RD2, and so on, although little change. Okay, so when you want very precise, right, and that's here we are talking in terms of I and V right now, right? You want to calculate I and V. So here when you calculate this using this equation, RD is automatically changing here. RD is this. ID is changing, RD is changing. But what parameters you are talking in terms of and what you want, accordingly you will use the equation. So let's say that here, if you are changing R, right, then in this circuit, if I'm changing R or I'm changing VDD, my ID will change accordingly. And if my ID is changing accordingly and I want to find out RD through this, then I will put it in this equation, this ID, and then I get RD of the diode. So if you are asked to find out the dynamic resistance of the diode, you do that way. Okay, and this graph already has your RD. Right, if this is the tangent, this is 1 upon RD. If I'm drawing a tangent across here, across let's say here, right, then this is 1 upon RD. But when it is conducting and you are drawing, that change is little. Here the change is still more. Okay. This is not perfectly so from like 0.7, all this. So yeah, this RD is a function of RD when you are talking of I and V. And if you want to find out precisely, you find out ID from these two equations, because two variables, two equations, and from that you get RD. But otherwise also this is RD, because you are talking of this and this, RD is implied, it is there. Okay, समझ में आ रही हो आप लोग?
Yes, ma'am.
I can go ahead.
Ma'am, can you please explain what is load line over here?
Yeah. See, what did I explain right now, up till now? That this line, how did you get, you understand? How did you get this line?
No, ma'am.
Okay. you are fine with this equation?
Yes,
Huh?
ma'am. Yes, ma'am.
This equation is this graph. Okay?
Okay,
E
ma'am.
raised to exponential. Diode no graph share. That you should be okay now. And now this is fine. This VDD minus VD divided by R is ID. Same ID is flowing. Do you
Yes.
accept this equation?
Yes, ma'am. Yes, ma'am.
Okay, good. Now here, what are we doing? Now this is your V versus I graph. Okay, and here you have this term. Okay, this term and this term is the voltage across the diode, and this. Okay, these are two varying. Here this is varying, this is varying. When I say V, okay, so here this V is from 0 to VDD, let's say. So once and now I and V, so this line is V is equal to 0 and this line is I is equal to 0. So in this, if I put I is equal to 0, okay,
Yes, ma'am.
if I put I is equal to 0, then V is equal to VDD.
Yes, ma'am. VDD. If
Apa
it's
ini આવ્યું?
yes,
Ini
ma'am.
આવ્યું? I is equal to 0, તો VDD આવ્યું?
Here we are plotting. Here we are changing the voltage across diode, ma'am.
See, this is this I, small I. Okay, and that is this V. Okay. So this V and this I. Okay, so now you make I 0 to get this point, two extreme points.
Okay, ma'am.
See, this is voltage across the diode. Yeah, this is voltage across the diode. When I say this V, this is a whole range. Now that whole range is what? This whole range is, it cannot be greater than this, your supply. Okay. This cannot be greater than the supply. So what I will vary is this point, I'll vary from 0 to VDD. This is your supply. Your this here, this voltage here cannot be greater than this.
Yes, ma'am.
Battery જે voltage હોય maximum હોય, એનાથી વધારે તમને સર્કિટમાં બીજું you don't get any other voltage higher than that.
And
So
here, ma'am,
this-
the supply is constant. VDD, we are keeping it constant.
Pardon?
Are we keeping the supply voltage constant, ma'am, here?
Yeah, this is DC only, but
Okay.
the DC also you can change now.
Yes, ma'am.
Let's say it is 1 volt, then 2 volt पे क्या होगा, 3 volt पे क्या होगा, that's what. So
Yes.
here your so now here this is V, your V. So this is the voltage across the diode is V, and that V cannot. What we are doing is we are varying this V. Now what is the limit from 0 volt to, let's say, what is the maximum? The maximum is this VDD. The maximum is this VDD.
Yes, ma'am.
Okay.
That I understood, ma'am. That I understood.
So you don't think this V, you take it. So this is this small V. But the diode, for diode, see, there are two things here. Two things here. One is R and one is this diode. Both have different lines, IV. Okay. So ये diode तो इधर तक ही है, that VD. Okay. But if you forget diode, okay, and if you are talking of the voltage across here, okay, and this, I mean, diode is there only, but here there is R. Now, if you are talking of this equation, what I mean to say is you forget this equation and we are talking of this equation and this sum drop. if you don't think diode, there is some drop, which is given by this equation. Then this is the line. You think these two lines separately. Okay. One is this equation, you have plotted this line. Another is this equation. Okay. This you give any name, X, Y, Z or VD. Then you will get this line.
Yes, ma'am. Yes,
ma'am. That's what. So you think that way both to be this. But you are varying this V is from 0 to VDD. So this is, if this is, let's say 5 volt, then you start from 0 to 5 volt. Then what is this V here? So see, if this is 0 to 5 volt, then what is this as a function of 0 to 5 volt here? If you put 0 to 5 volt here, let's say, right? So it is not, it is going to give you this relation. It for whatever 0 to 5 volt or 10 volt or 1 volt you keep, it will give you this relation. Okay, if you are doing this from 0 to 0.5 volt, then it will be, if here it is 0.5 volt, then your graph will be only this much. Okay, but this is something 3, 4, 5, 10 volt, then it is showing. But your graph diode will be limited this much only. Whatever this VD, right? Even if it is 0 to 5 volt, you are changing, then this is your diode equation.
Yes, ma'am. That is, we are plotting the means along the x-axis we are plotting the voltage across the diode, and along the y-axis we are plotting current across the diode, right, ma'am?
Yeah, but it is not just diode. R is also there.
Means the current will be the same on.
No, you are changing this. In simple case, what do you think? You are changing this. See, you are changing this. This is, let's say, maximum 5 volt. You are changing 0 to 5 volt. Then what is this V here? This V, this is V, and this is I. So you are plotting for change of this, you are plotting this and this versus this for this equation and this equation. Is that clear?
Yes, ma'am. Now it is clear, ma'am.
So for this some value, we are starting from 0 to that value, and you are seeing this voltage, that is V, for this I. And and then these are for these two different equations simultaneously. So here also, if you put, as I just said, one time you put this 0, when this is 0, right, then IR is equal to VDD, right? So yeah, so I is equal to VDD by R. So that is what. See, even if you have 100 volt or 200 volt, the drop here will be. So for diode, it is this equation only. Whatever the voltages are there here, the diode will be always, and then it will break down, of course. You cannot give too high voltage, it will break down. Yeah.
Yes, ma'am. I understood. I understood.
Okay, so now we go one step ahead, and there are, like, the diode, this is normal diode. There is another kind of diode that is known as Zener diode. And then there is Zener diode, and then LEDs, and a lot of organic in your TV, this TV, OLED TV, we have OLED, right? Those kind of organic light emitting diode and all. There are a lot of, we'll see there are different diodes, but this Zener diode is one of the very important application. This diode is in all your power supply. So as I talked to you last time, that from the point where your electricity is generated, okay, it is thousands of kilovolt that passes through those transmission line. And in India, it is 230 volt. In Europe, USA, it is 1110. So it has to be stepped down. And then every electronics now is IC, it needs mostly all application needs DC. your phone, your laptop, your TV, whatever. I mean, wherever, especially ICs are there, and your fan works on what, AC or DC? So next time, let me know the list of the appliances that works on AC, and you will find out that mostly everything works on DC. So now, and then your AC has to be converted into DC, okay, because from the source it is AC, and I explained you last time why it is AC. We can also have DC powerhouses that generates DC signal, but those are, wherever you use it, you generate it. It cannot travel long distances. So AC is generated, and we use DC, so we have to convert that. But these are thousands of kilovolts of high voltages that are passing through the transmission line, and we don't need that. There will be big blast otherwise, okay, and everything will get destroyed. So we have to step down that. We use transformer, and because transformer was invented, and at the same time all this electricity, hydro, and electricity from hydro and everything we were getting. But if there were no transformer would not have been invented, then also everything would have been in vain. So transformer it will still keep AC only, but it will step down your high voltages. And then we convert this step down as per our need into the DC. You need 5 volt, some ICs need 10 volt, whatever, 1.8 volt, 3 volt. So then we need accordingly the DC, but your signals can fluctuate. Your AC will fluctuate, then your DC will also fluctuate, and then everything will be destroyed, right? So every IC has a power circuit, okay, power unit. Your TV, your laptop, your phone, everything has a power unit, and that has to be designed such that irrespective of the change, and especially when the fluctuation, it's just a spike for a microsecond, but it will destroy your device. And that we are smart people, and we have figured out a way, and this Zener diode is there in all power circuits. And what is the use? The use is to regulate the voltage. Voltage regulation means if you need 3 volt, it will give 3 volt only if even there is a fluctuation. Your IC needs, let's say, 3 volt. Okay, your phone to charge needs, let's say, 10 volt, for example. Okay, then it will give 10 volt only, even if there is a spike for a microsecond, for a millisecond, let's say, and it goes to 100 volt, let's say. Then what? Your phone, you have to garbage it? No. It will ensure that still, even in worst condition, it gets the supply that it is designed for. And for that, there are different capacities of Zener diode. We use this as a voltage regulator, means in spite of the fluctuations, it will give out a constant voltage. And this is a diode, and the way it works is little different. Of course, that's why we are studying. And as you can see here, that this is the symbol where instead of that line, it is Z. Z is for Zener here. And as you know that the normal diode in the reverse bias, it breaks down. If you make it use in a reverse breakdown region of a reverse bias, where voltage you give and you make it work, it gets destroyed and you have to garbage it. But this guy is intentionally made to work in the reverse breakdown region, although it can operate in a forward region like the normal diode, and it will show you the same characteristics. Okay, it will have the same characteristics, but this is an expanded view. Once again, I'm telling. So if you make that Zener also in forward, it works like this way only, but it is intended to work in the reverse breakdown region. And that's what we are going to understand today. Okay. So once again, understand it is like a normal diode, but an added advantage is it works in the reverse breakdown, and that is what it is meant to do. Otherwise, if you want to make it use in a forward, we'll use normal diode only. You don't need a Zener diode especially for that. And where you need voltage regulator, we use Zener diode. So that is first thing. The symbol is another thing. And as you can understand, it works in the reverse breakdown region. Okay, so the direction. So in the normal diode, this was the direction of, this is the direction of the flow of the current, right? So it will flow this way. This is breakdown, so this is in the opposite direction. So for the Zener, the current flows in this direction, right? So this is anode, this is cathode, this will flow from cathode to anode. In normal, it is anode to cathode. Into cathode and leaves anode. So this is cathode to anode. And manufacturer, they will specify. So you, with this diode, you get a data sheet and they will specify the Zener voltage. So there is a voltage, that is Zener voltage, we say VZ. So at which it breaks down, and let's say 3 volt, then at the 3 volt, it will pass high current. And below 3 volt, it is not conducting. Okay, so that's what it means. So this is Zener voltage. We'll see all this, say 2.7 volt at 10 milliamps. So they will give the Zener voltage and a test current. So what is the current at that voltage? And it will also define the dynamic resistance. From that, you can find out the dynamic resistance of the diode. So we will see into detail this. I had talked a little, but now you have to understand properly how the Zener and the physics behind that, what is that, and the application of that. That's what I'm going to teach you shortly. But is that okay? So this curve you are very much aware of. Now we are targeting is Zener, and as you can see here, this is the reverse, and and this line, you know, it is little bit, it has a slope. It is slanting. It's not a straight line, although, as I said, an ideal line is a straight line, but we don't get anything ideal. This is a practical one. It has a little slope, and this slope shows the resistance. Now you are understanding, right? And there is a resistance involved. Now, when you see this curve, this is in nano to pico nano range, and almost we say this is off only, not almost. This is off condition, but although practically there is a nano pico ampere of current. But then after this voltage, that is VZK, that is Zener knee voltage, it is like this shape of our knee, leg, knee, right? Knee, that button bolte na, that knee shape. So at this point, then there is a rise in the current, and this is known as this Zener knee voltage, right? At which point, at that point, after that, the current will rise steeply. And what the data sheet contains, this is the Zener voltage at which we operate it. Okay, application I will shortly show you. So this is the voltage at which we operate, and you can see that there is a decent good current in milliampere will flow. So at this voltage, let's say some current will flow, that is a test current, that is also given. So the operating voltage at which it operates is given, and for that there is a corresponding current to that, and we say that is a test current. Okay, and now you can understand this line is almost linear. So if you draw a linear, if you want to find out a slope, it will cut this x-axis at this point. Okay, and that is known as VZ0, where this linear line, the slope cuts, and that is VZ0, although VZK and VZ0 are almost the same, but they are still different. At this point, at Zener knee voltage, is an exponential rise in the current, and the current from that point rises steeply, and this is where it intersects this line, that is VZ0, and this is the operating voltage here. Now, you can see also that for a current, that is this is the line for the current, okay? So, and it operates in the reverse bias. So we are talking of this third quadrant. And if the current is changing from here, and so that is this to here, for this much change in the current, okay, from here to here, that is delta I, the delta V changes, right? So this point to this point, okay, so this is the change in the delta V. So for this little change in delta V, you have a huge change in the current, okay? And this relation, it is given by I, and V is given by delta V is equal to delta I into RZ. and that RZ is given by the inverse of the slope. Or you can say slope is equal to 1 upon RZ. This is a straight, almost linear line. When you draw a line and you take out the slope, it is 1 upon RZ, and it will cut here at VZ0. And this is the relation for a huge change in current. We get for huge change in current, this is the change in the voltage, and the relation is delta V is equal to delta I into RZ. Okay, so this is the Zener voltage and resistance RZ. And this is simple, easy to understand. I hope this is making sense to you now. Although we wish that this be a straight line, but nothing is ideal and there is a slope involved, and slope means there is R involved. And this model will be given if you want to do a model, show a model for this. Then it is VZ0, this voltage, okay, that is this VZ. So the Zener, the voltage VZ is this VZ0, and then this resistance involved. So, and the total voltage is IZ RZ. Okay, so this VZ is VZ0 plus IZ RZ, where this is VZ. This VZ is equal to VZ0 plus this IZ RZ, where IZ is the current that is flowing this. Okay, so it is given this way for IZ very, very greater than IZK, of course. So IZ is the current flowing at this VZ, this IZ, okay, when it is VZ. But that VZ is given by VZ0 plus this. This is the thing. This voltage across this is the model, and this is the fixed voltage VZ0 plus RZ into this IZ. So this two voltages, this voltage is IZ RZ. The same current is flowing. And they are fabricated for few volts to few hundred volts. Okay, so it depends on the capacity. It's a huge variation and depends on the application, what you use. And here IZ is very, very greater than IZK. Okay, so this, because of this is IZK. So this current, when it is conducting, it is really, really higher compared to this. And VZ is greater than VZ0, as you can understand now. So I'll explain you the difference, why it is not breaking down, why doesn't it get destroyed. But before I explain you that, let me explain you, if still the time doesn't remain, let me explain you the application, means what do you mean by a voltage regulator first, then I go to the physics. So let's say that this is a simple application where you can see that this is a source, a battery, which is from, let's say, 1 volt to 6 volt. Okay. And this is an LED, this is 3 volts. So this is an application. It can be another circuit also, any load. Okay. But here we are just considering LED, a simple case. And what does it mean? And there is a resistor to protect this LED. Otherwise, if you directly connect it, it will get destroyed because there is no control. As I said, this resistor will pass the current, okay, which will save this LED. Otherwise, there is no control, and then this will get destroyed. So the resistor is there, and 1 volt to 6 volt, and this is 3 volt LED. Now, if you give voltage higher than 3 volt, okay, to make this on, it needs 3 volt. If higher than 3 volt falls on this, it will get destroyed. Okay, this LED will destroy. You cannot give a higher voltage than, right? Because this has a capacity. It has some capacity. If a higher voltage falls, it will get destroyed. So that is the operating condition, the voltage, right, that it needs. So what we do that, let's say now, instead of like 3 volt it needs, this is fluctuating and this is set to 4 volt, 5 volt, or 6 volt, then what will happen? This will get destroyed. So you can think this as your another application, let's say a phone, okay, and then it gets destroyed. Then what, you will garbage your phone? No. So we have a way out, and we have to prevent the circuit from getting destroyed. And whatever the voltage it needs, it should get. It needs 3 volt, it should get 3 volt. And even if it is fluctuating, it should still get 3 volt. So even if the battery is 5 volt or 4 volt, it should get 3 volt. Okay. So to do that, what we do, that we will have in parallel across this LED, right, which is your load or your circuit. Here it is LED, a simple case. We will connect a Zener diode. Okay, we will connect a Zener diode, which is a 3 volt diode. It means it is conducting at 3 volt. Okay, so it starts conducting at 3 volt. So now you have two cases here, and the connection is this way. One is that this is 1 to 6 volt. This is 3 volt. Zener is 3 volt. Let's say that if it is less than or equal to 3 volt, your battery. Okay, less than or equal to 3 volt. And then the other case is greater than 3 volt. Case 2 is greater than 3 volt. Then if in case 1, okay, if it is less than 3 volt, your Zener is 3 volt and your supply is less than 3 volt, then what will happen? See, this is less than 3 volt, okay. This is, it can be 2.9, it can be, right, so around 3, but it is less than 3 volt, case 1. See, if it is less than 3 volt, then what will happen? Your Zener is not on, okay. So it is almost 2.93 volt. So your LED will on. Okay. And this is off. But now let's say it is greater than 3 volt. So it is 4 volt, 5 volt, or 6 volt. Then what will happen? Whatever the voltage is, okay, your Zener, when it is 3 volt, greater than 3 volt, then this guy will start conducting. And see here, what does it mean here? That even if your current is varying so much, your voltage is almost constant. This voltage is almost constant, okay? So huge change in current will not change the voltage. We want, what I said initially, we want things ideal. If a straight line hota, so it was perfect. But we don't get a straight line, right? But whatever the voltage is for this current, this voltage will remain constant. Okay, so for a huge change in current, the voltage, even if it is like 3 volt, then for this current, it will be 3.01 or something. There's not a huge change in, yeah. So if this is 3 volt, then this is 3.01. It's almost the same only, okay, for a huge change in current. So the point here is that, so now if it is 6 volt, let's say 6 volt, was we take, then what will happen? If directly this Zener would not have been there and we give 6 volt, this will get destroyed. Okay, but now the Zener is there and you are giving a 6 volt. So what will happen? This will still give 3 volt. Okay, and the 3 volt will appear across this LED. Now what is changing? Even if this R is same, all these things are same. If this is 2 volt or 4 volt or 6 volt, because of that, now this drop is constant, 3 volt Zener. 3 volt is constant. So if it is 6 volt, then it is 6 minus 3. So 3 volt. So this I flowing current, changing current is changing here, nothing else. Okay, as per this change in this voltage here. So if it is 5 volt, then it is 5 minus 3 divided by R. So that I is flowing. If it is 6 volt, then 6 minus 3. So 3 volt divided by R. If it is 3 volt, then so 2.9, then so that way, right? So if it is 3 volt, then what is flowing? If it is 3 volt, then so how is Zener operating? Zener is operating at 3 volt. Okay, so 3 volt will appear here. This will be 3 volt only. This is constant. For less than 3 volt, it is not there. So this will not get destroyed. But when it is greater than 3, this voltage here, this will remain 3 volt only. But what is changing is I. So that's what I'm showing you here. What is changing is I. But still the voltage is almost constant. That is 3 volt. So every time, even if it is exceeding 3 volt here, right, still the voltage across the LED will remain 3 volt and it will remain on and it will be protected. Understood, or still I need to explain you? Jaldi bolo.
Understood, ma'am. Understood, ma'am.
Zener is for voltage regulation, meaning that whatever is your load means your circuit. It can be your TV set, it can be your phone. The voltage, DC voltage should be same. Now it may happen that because of the change in the AC or DC will also fluctuate, right? But then it cannot destroy. We have to prevent it. So this is a preventive measure where this is connected in parallel. If the voltage is less than this needs 3 volt, so this capacity is 3 volt. Okay. આ 3 volt ની LED છે. That's why we have taken this 3 volt. If this was 5 volt LED, we'll take this 5 volt. So for less than 3 volt, this will not get destroyed even if it goes down. Okay, that is one thing. So for less than 3 volt, this is not working, and whatever it gets, so it 3 voltage, sometimes there are fluctuations. So if it gets less than that, then this is still this is not this doesn't get destroyed. Okay, and then let's say for a time being, for a microsecond, if it gets to 4 to 5 volt, still this voltage will remain 3 volt only, and it will protect this from getting destroyed. Okay, it has a capacity. This is a small excuse me. This is a device which operates on a voltage. If you give very high voltage, it will get destroyed. So this is protecting this, and it will limit the voltage across this through 3 volt, whatever the change may happen here. Okay. So physics, I'll explain you next time. That why doesn't happen.
Yeah, in this slide, what if you apply voltage law like the LED bulb and this diode, both are parallel and both have 3
remember,
volts.
first thing, daily watt samajh. If this will be conducting, okay, this will be conducting for, see this graph you understand. Graph. Okay. So you understand this VZ. This is a Zener diode. Let's say this VZ is 3 volt. It means that it is conducting at VZ, which is 3 volt. So at 3 volt, it is conducting. Okay. Every Zener has a conducting voltage. Conducting means current is flowing. Okay. So, and then there is some voltage. Now, below this voltage, it is not conducting. बराबर ने 3 volt हो तो 3 volt या conductor से below that it will not conduct. And do you agree or no?
Yes,
Same thing. This is 3 volt Zener. It will conduct for 3 volt, okay, and not below that. Yeah, and across this is the voltage. And then another thing you see here, that even if the voltage is high, okay, see, below this 3 volt, it will not conduct. If it goes high voltage, still, it will remain conducting at 3 volt only. Voltage मान के high gayo across the Zener. If this voltage goes to 4, 5, 6, it is still conducting at 3 volt only. Is that clear from this graph?
Yes, ma'am.
So now you forget LED, you just think of a Zener and a supply here. So if it is conducting, if it is less than 3 volt, will it conduct or no?
No, it won't.
No, it will not conduct, right? From the graph, you understand?
Yes, ma'am.
Now, if it is 3 volt, it will conduct. If it is 3.5, it will conduct 4, 5. But the voltage across, even if this is changing to 4, 5, 6 volt, this will be still 3 volt or no?
Yes, ma'am, understood.
That's what. Okay, anything else? Anybody, any queries? Because this will take time. I'll explain you next time. See, things are simple, but you have to understand here what is changing is this current. Even if, because this is constant, this is changing, the difference of this is changing, the voltage, and hence I is changing. That is what, even if that I is changing huge, this I is changing from here to here, still the voltage is almost the same. That's the beauty. Okay, so what is changing is your I, but still your voltage will remain almost, and that is the capacity of the Zener. Whatever the change in current happens, voltage will remain same, almost same. એટલે આનું 3.1 ની બદલે 3.1 થયું માનો, right? Because of this there is a change. So from 3 volt it has gone to from here to 3.1 volt, but that 3.1 volt will not destroy all this. Okay, 4, 5, 6 volt will destroy. So little 1-2% of fluctuation will not destroy, at least. Are you getting?
Yes, ma'am.
Any queries now? And that
Ma'am,
we
in the
will see you want a straight deep.
Ma'am, in the previous, ma'am, in this slide here, when the voltage is less than 3 volts, ma'am, this slide after this.
Destroy nahi thai. See, if it is 2 volt, it may not light up, or it will dim light thase. Okay, if it is just
question is
1 volt, it will not light up, but it will not get destroyed.
Yes, ma'am. My question is regarding this slide after this slide. Yes, ma'am. Ma'am, here when the voltage is less than 3 volts, the current will flow only across the LED, right, ma'am?
Yes, this is off. And that is
at
fine. That's what we want. It will not destroy. Even if it is low, it will dim or off, or it will be on. If it is perfect maximum 3 volt, it will be fine. It is running. But once it climbs that, 3.1 is also fine. It will be still on. But let's say 4 volt, 5 volt, so in that case, this Zener will start conducting, and it will, whatever the voltage here is, it will still be 3 volt. What will change is the I here. Okay, so here 6 volt, here 4 volt. So what will change is I. This will remain 3 volt only.
At exactly 3 volts, the current will be 0, right, ma'am?
No. See, now this is conducting at 3 volts, or greater than 3 volt, it will start conducting. So at 3 volt is given here. This is not conducting. This is like not there at 3 volt, let's say. 3 volt conduct thwa mande, so 3 volt sudhi nothing. This is like not there, and 3 volt appears here. Once this is 3.1, it will start conducting. Okay, 3.2, it will start conducting. Do you understand?
Yes, ma'am, I understand. My question is
so let's say 3 volt also it is conducting, but it will give 3 volt only. So this guy will get 3 volt only.
Yes, my question, I was just wanted to confirm that will the current will be 0 across the circuit?
No. Okay. So when this is 3 volt here, okay, this is conducting or not conducting. If this is 3 volt, it will be 3 volt, and this is not conducting. If it is 3.1 or 4 volt or 3.5 volt or 5 volt, whatever is here, this will be still be 3 volt. So if it is 3.5 volt and then 3 volt, then difference is 0.5 volt. So this is your I is equal to V by R. So 0.5 upon R will be the current flowing. If this is 4 volt, then 4 minus 3 is 1 volt. So 1 volt upon the value of R will be the current flowing. If it is 6 volt and this is still 3 volt, as I said, right? So 6 minus 3 volt upon. So this current will change depending on the voltage here. This will remain 3 volt only. And even if it is 3 volt here and this is not on, or let's say it is just on, then still it will be 3 volt here. So even if it is 3 volt here, right? And this is 3 volt that is given here, right? So this will still remain 3 volt only.
So when they means by at that point only, when the voltage source is at 3 volts, the voltage across the Zener diode is also 3 volt, and the voltage across the DC source is also 3 volt. Then the current will be 0, right?
No. Current,
Yes.
it will not be completely 0. So let's say this is 3 volt. Okay. This is off. So that 3 volt goes here. Okay. So this is off at 3 volt. So that 3 volt goes here. Okay. So the current is flowing. So this is there is no, this is not there. At 3 volt, this is not there. Okay. For you, samjhao. Don't get confused and don't see at 3 volt, right? And when this is 3 volt, this is not conducting. Okay. This is like not there. Okay, and the current flows accordingly and it will be on. Now let's say 3.1, 3.2, 3.3, it will start conducting, and this voltage across this will be, it will get this voltage and voltage must say 3, this 3 volt it will give. Once it exceeds 3 volt from here, it will start conducting, and whatever the voltage here is, this will get constant voltage. And 3 volt. But my point to you was, I was explaining you from Zener point of view, okay, what is going on inside the Zener. So less than 3 volt, it was not conducting. Greater than 3 volt, it will start conducting. And what will change is the voltage will remain almost constant. What is changing is the I through the Zener.
That I understood. That I understood.
But here for less than 3 volt, this is giving, this is not athlete circuit. Less than 3 volt with change. Okay, and greater than 3 volt, you think this as your this thing for LED, from LED point of view. This is giving the voltage. Barabar na?
Yes, ma'am.
And I was just, yeah. So it is not mistaking. You just think, separate out your concept and divide your this voltages into this. When this is not existing, this is giving the voltage. And when this is on, this is giving the voltage to the LED. But from Zener point of view, how it is working is that once it is on, and if this is changing, the current is changing. The voltage will remain same. That's why I moved to that graph and show you. Okay?
Okay, ma'am.
Sorry. Thank you.
Thank you, ma'am.
Yeah.